Welcome to ExplainerCast Episode 7. I'm your host, Dave Smith.
And this is Shane Swenson.
We have some explaining to do. Okay, we are continuing the saga of how to communicate at a distance. Last time we left off with the invention of the telephone, where we could transmit voice communication over long distances, thanks to some serendipity when trying to transmit multiple telegraphs over long distances.
Yep.
And today, we're going to take that to the extreme.
That's right.
And we hope that we'll end up on a fun fact that many of you will recognize, a fun number that many of you will recognize, and now you'll know why that number is the number that it is.
Sounds good. So I think if we were to start with where we were last time, we were talking about Alexander Graham Bell. And again, he was originally working on what he called harmonic multiplexing of telegraph signals, which was essentially trying to send multiple different tones or pitches of independent, what we would call wavelengths of signal or frequencies down the same wire. And so he had some apparatus where he had essentially the ability to create a vibration on one end, and specifically an electrical vibration. Then the circuit would carry that electrical vibration, and on the other end, it would cause a particular receiver to activate, essentially a receiver that was tuned to receive that same vibration.
Right, and ignore all others.
And Dave, I don't know how many of our listeners are from the generation that grew up with tunable radios, but like if you had a radio in your car and it had all the different frequencies or channels on it, essentially that's what you're doing is you're selecting which frequency of vibration electrically, or in that case, in the electromagnetic spectrum and the radio, that you're actually listening to. And so each station could transmit on a different frequency. And essentially he was one of the early people doing that on wire with small numbers, like a handful of different transmitters and receivers. And apparently what he noticed was that you could receive more than just one tone at a time. You could actually receive a more complex signal. And apparently something I didn't realize before, but Alexander Graham Bell had done a lot of work studying human speech and working with people who couldn't hear or needed other accommodations. And so he knew a lot about the human speech system. And so apparently when he saw just some of these vibrations coming through his system, he recognized the potential to try and map that to vocal audio.
That's so cool. He was like, oh, yes, electricity can vibrate.
And we asked last time if he had like a microphone, and he didn't originally, but once he realized instead of transmitting telegraph signals, he could transmit vocal speech, he did build some things that look a lot like what we would consider microphones today. He took some type of a diaphragm, like a piece of stretched material over an aperture, and attached it to some type of a wire, maybe with a magnet nearby. And as it vibrated, the movement of a magnet near a coil of wire will cause the magnetic field to move through that coil of wire in a way that actually induces an electrical current in that wire. And this is one way that microphones work, is as we speak, it causes that diaphragm to vibrate. It activates this magnetic coupling to some coiled wire and causes a small electrical current to flow. And if you then take that signal and you amplify it, make it more powerful, and then use that signal to activate an electromagnet to essentially vibrate in the same way and have that electromagnet move another diaphragm, you've built what we call the speaker. And now you've taken sound waves that were spoken by one human being. They were converted to an electrical signal representing the movement of the diaphragm that sound wave hit. And then somewhere else, you use that electrical signal to move another diaphragm in proportion, which creates more sound waves that are ultimately heard in the human ear as that original speech.
So cool.
So he figured out how to take sound from one place and transmit it over a great distance electrically, and then reproduce it in another place.
That is so cool. This is one of the coolest things to me because it's a reminder that every microphone is itself a crappy speaker, and every speaker is itself a crappy microphone, because they're basically the same fundamental components on both sides, right?
Yeah, it's just really which direction are you going from pressure waves to electrical signal, or from electrical signal back to pressure waves.
The other thing that I think is really cool to imagine here is this microphone contraption is actually it's like a little parachute that's designed to capture the force of the sound waves coming out of your mouth and impacting it, and then just move.
Yep.
Just move. And it turned, to me, this is, I don't know. I don't know if Alexander Graham Bell was a pioneer in this space, but understanding that human speech, and frankly all sounds, are actually composed of all these little micro vibrations.
Yep.
Which, when packed in sequentially at different frequencies, create all the sounds we can hear.
Yeah, and I don't know when the math of waves and superposition and frequency analysis and sort of what we would call spectral analysis of the frequency components of a signal, I actually don't know when that was all being discovered, but it's all super relevant to both of these phenomena, both the sound waves in the air and the electrical signals, these alternating, oscillating electrical signals being carried by the wires. So in the development of these technologies, certainly that type of mathematics became very important and would have had to be pushed forward in the process.
Yeah, it's so cool. And he had to understand amplification as well. So certainly he had at least a theoretical understanding of the waveforms and how, the height as visually represented, the height of the wave is volume, and the tightness of the wave correlates to frequency. And he knew that there was no way that this little tiny motion of these wires coming off of this diaphragm against this near a magnet could possibly have enough energy to transmit over the distances that he wanted to transmit. So he had to invent or buy off the shelf amplifiers.
That's right.
Which I guess kind of existed already, but now I got to ask you, with telegraphs, the amplification systems were very much, I don't want to say digital, but they were discrete, right? Because it was incoming click, then gets retransmitted as a new click down a non-contiguous piece of wire that wasn't actually connected to the original wire. But now with telephone systems, that needs to be a totally different approach. If the electrical signal of your voice hits one of these telegraph relays, it's not going to continue.
That's right.
So how did they get through that?
Yeah, so they would have had to come up with technologies that rather than just directly regenerating the ons and offs that the telegraph utilized, would instead take all the different oscillations and complex behavior of the signal, the transmitted voice signal itself, and essentially you try to create a higher power version of that exact same signal. And so this is called amplification as opposed to regeneration. Regeneration meaning I'm going to make a new copy of the original digital signal. Amplification meaning I'm just going to make it kind of louder, or in the electrical space, higher power. And so you can make analog circuits that do this, that essentially a small input coming in results in a big input, of the same proportion going out. And there are limits to this. Those types of amplifiers almost always add noise.
Yeah.
And so over time you'll gain more artifacts and sometimes like a hiss or a buzz or other background sound that you have to deal with as well.
Yeah, because you're also amplifying the inherent noise that's in the original signal too, right?
Yep. And the amplifier itself has usually a noise that it's going to contribute as well.
Yes, that makes sense. I was kind of thinking, and maybe I've got this wrong, but as the original signal travels down the wire, it's losing amplitude or power as it goes to resistance, right?
Yep.
And so, but the noise floor on that wire, I'm assuming must be kind of constant. So when you then receive that signal, the signal to noise ratio, literally the height of the signal wave compared to the height of the noise mess down at the bottom in a waveform, is lower. The ratio is lower. And so when you amplify the resulting signal, you're actually amplifying noise and signal, but the ratios were worse when it got there. And so you're adding not only noise from the circuitry, but also inherently there's more noise because you got to boost everything.
That's right.
Or is that not true? Did they have the ability to filter out noise at this point?
I would assume it would have been pretty rudimentary. You could create a filter that would at least filter out like high frequency noise above kind of the frequency of spoken voice you wanted to carry.
Yeah.
But the trade-off you described is an important one that still persists in transmission line systems today. If you have like a very long haul, multi-hop like radio link or maybe a fiber optic link, there may have to be amplification stages along the way. And you don't want to put too many amplifiers in because they're expensive. They each require their own power source, their potential points of failure. and they each do contribute their own form of noise to the amplified signal.
Mm-hmm.
On the other hand, if you space them too far apart, then by the time you're re-amplifying the signal, if the signal to noise ratio has gotten low enough, if it's bad, you're now amplifying more noise than you want to. So there's often kind of a sweet spot as you're designing a transmission system that says, I want to gain as much reach as I can for each segment, but I will make sure I don't let it get too far down before I re-amplify so that I still have good signal to amplify in the first place.
So we've now got ourselves in a situation where Alexander Graham Bell has created a means for transmitting voice over the same wires that we're transmitting telegraph signals, but now we got to swap out more infrastructure, right? So, we went from wooden towers with no wires to wires, multiple wires, to single wire with relays, and now it's like, oh crap, we got to revamp again. So it's just very interesting to think how many, the same physical location on Earth, how often it has been revisited to upgrade the infrastructure on it.
Yeah, for sure. And because you would have gone from maybe single wire telegraphy with ground return to dual wire. So that for the telephone, they would use a pair of wires to ensure they had much higher quality than ground return provided. So using twice as many wires. And then, you have to replace any of those relay-based regenerators that worked for telegraph signals with a full spectrum amplifier if you need to power up the signal. So you end up replacing almost all the physical plant. They probably had better quality wire too while you're at it.
Yeah, better insulators.
Yep, better insulators, so forth. And yet, you would use in many cases the same right of way, maybe the same set of wooden poles that the wires are hanging on, and then later they would have replaced those wires with better wires, eventually maybe with coaxial cable, which could carry a lot more electrical bandwidth, meaning more signal information at the same time. And then, of course, today, if you were putting in modern terrestrial network equipment or any type of conductor-based communication equipment over any long distance, you're going to use fiber.
Mm-hmm.
Again, another wave of replacement as that technology came online.
Yeah. And we will get to fiber eventually, I think.
Yeah, I think so. I think we got to get there eventually. I don't know if it's today, but we will.
Yeah. Okay, so now, of course, another round of amazing technological innovation. People can hear the voices of their distant loved ones as if they were standing right in the same room, except really kind of a crappy version of their voice, right?
Yeah.
I mean, you've heard some of these sounds. They didn't sound great.
Right. And there's probably two different caveats. The first one is initially the distances would have been relatively modest, at least for the things that people could afford if they weren't a head of state or a very large business.
How long are we talking?
Thinking about the way that this got deployed, I'm thinking like the rural United States, and you see examples of this like in old TV shows where they had a party line, and essentially they'd run wires sort of from house to house to house along like a country road, and those people would all share the same telephone circuit. And so if your phone was on a hook, meaning you weren't using it, essentially it would be bypassed by the telephone circuit. If you pick up the receiver and it's off hook, now you connect into the circuit. And along that whole party line, if anybody spoke, everybody who had their earpiece off hook could hear it. And so you really had to take turns. There was no privacy on this thing, but it was the minimum amount of infrastructure to connect all of those people together.
Yeah.
And I think the radius on those would have been measured in 1s to 10s of miles.
Okay.
Not that far.
Yeah.
But enough to connect people, again, in the same town that would have a reason to want to talk to each other. It still beats walking a mile down the road to your neighbor to check in on them, for example.
Absolutely.
And then that party line could come into town, into some type of a central switching station. And this over time became called a central office, where imagine the lines coming in from all these different party lines, and then maybe later each subscriber gets their own direct connection to the central office, so that they could then connect their telephone to any other subscriber's telephone in that local area. And so think of this now again as in a single town, say, and to this day, if you look at a telephone number in the US, the last 4 digits represent which of the lines were coming into a given central office. So The central office architecture was designed to handle up to 10,000 subscribers. And so you needed 4 digits to represent that. And that's what that last 4 digits in your dialing represent. So that lets you connect at a local area. And initially that was done with a manual switchboard. You'd pick up your phone and an operator would see that your phone was off hook via like an indicator light. And they would check in and say, who are you calling? You'd say who you're calling. And they would make a connection in their switchboard from your circuit to the person you're calling circuit, ring their phone, check to see if they're available, and then you could talk. So Alexander Graham Bell invented this, I think, in 1876. And by the 1880s, people were developing automated switches where instead of having to talk to an operator, you could actually dial.
So cool.
And they initially had like this rotary dialing that maybe if you've seen an old telephone, it's got on it where each number would send a different number of pulses, electrical pulses down the line.
Yep.
And those pulses signaled to the electromechanical switch how to select which subscriber you're trying to connect to. And so as you dialed those 4 digits of the subscriber, it would configure 4 switches, one for each digit, to then select the exact correct phone call or the exact correct phone line out of the 10,000 possible options in that central office to then ring out and make the connection to.
And when you say select, we need to be clear here. We are talking about actually connecting physical wires to each other.
Yep.
Through a series of switches that all happen automatically based on these pulses that came through the line originally.
Exactly. Yeah, so there was a type of switch called a Stroger switch. It was invented by a guy last name Stroger. Or Stroger maybe. And essentially the way it worked was each pulse would cause it to rotate like one click and make contact with a different wire coming into it on 10 different terminals. And then the second digit would change a second switch, 10 clicks. And so the combination of all these was then used to select the exact physical wires that you would ultimately be connected to through this network of switches.
So cool.
So that was all for local area. So again, think, I don't remember, 15-mile radius or something like that. 10,000 maximum subscribers. If you have more than that number of people, then you need multiple central offices, one for each kind of group of 10,000. And so then the next thing was, well, what if you wanted to talk to somebody who's farther away? Maybe they're in the next town over and you'd really like to talk to them on the phone. And so the next piece of technology is an interconnect between central office locations. And these were called trunk lines, because if you think of like a tree and all the branches go out to the leaves, which is the end users, the subscribers, then the trunk lines would interconnect clusters of branches, interconnect these central offices. And so some number of wires would have to be run between the two towns. And now when you dial in, initially you talk to the operator and you say, well, I'm trying to call so-and-so in the next town over. The operator would then first connect you to a trunk line to the other town's central office. And then the operator in that central office could make the final connection to the subscriber. With automated dialing in the US, that's what the 3 digits that come before the last 4 represented was, in my region, those 3 digits represent which of the central offices is the person I'm calling connected to. And so different sets of 3 numbers there would be mapped to different central offices, and you'd have one for yourself. But then if you were going to connect to another central office, it would be a different 3-digit code in the US numbering plan, and then followed by that 4-digit subscriber identifier within that office.
So cool. It's so cool. And I like to think about how we went from having operators at the edge nodes with telegraphs,
Yep.
where you would go to an office, give them a message to deliver, and then they would deliver it
Yep.
for you by clicking on the machine. And then with telephones, we moved the operators into the interior of the network, and the edge nodes were subscribers, regular people.
Yeah, self-service, really.
Yeah, kind of more self-service, but still some assistance needed in interior. And then we just got rid of all the people altogether.
Yeah, with the automated switching systems. Yeah. And again, if you were operating one of these networks and you started to look at your costs, your very first cost is the wire, all this infrastructure, this right away. Your next cost is all this equipment you're putting in. But then you start looking at your operational expense and all of the people that you have to staff round the clock just to provide all of the call setup and tear down. And so, yeah, automating that so that it would be reliable during the day, in the middle of the night, and you just pay for the capital expense and then the equipment maintenance. That's the way that most of these networks relatively quickly, moved into automation.
And I've seen some of these offices. I've seen videos of operating exchanges that they are just full. They're like rooms full of mechanical gears and drive shafts and clutches, and they're loud and they click, and every time someone comes in and makes a call, all these things start clicking and going crazy, and even when no one is actively dialing, you can hear just the spinning sound of these giant rotating shafts that the various switches would latch onto in order to move themselves to a different wire and make a different selection.
Mm-hmm.
It is actually awesome. Now, I doubt any of these exist anymore, but I saw a video on YouTube many years ago, maybe 10 years ago, from one that was surviving still in Spain.
Nice.
I'll have to pull that up maybe and see if we can post that on Twitter or something.
Yeah, the way that, engineering was done in that kind of industrial revolution era is really interesting, because it's so forward facing when you get to see it like that, and you can see exactly how it's working. And yeah, the sources of power coming in through, rather than having electrical motors or in every device, you provide like a rotating shaft, like you said, that they just clutch onto. It's pretty remarkable.
It is so cool. I really feel like we've lost something of the art in some of our modern technology, where so much just happens that the naked eye simply cannot observe. It happens on a piece of silicon.
Yeah, it's hidden.
Yeah, it's completely hidden.
Yep.
Whereas back in the day, it was raw and in your face, and it was honestly really beautiful. And I got to tell you, every once in a while, I think I was born about maybe 100 years too late.
that was your aesthetic, was like,
oh yeah,
big typewriters and big machines doing industrial
big mechanical
scale
machines.
Yeah. Yeah, it's remarkable, again, using the tools of the time, just how much of the same services we still use to this day, though, just at maybe higher rate or higher fidelity, were able to be delivered, first regionally, then nationally and globally, when that technology was quite new.
Yeah, and in fact, so in the United States, we still use the same exact 10-digit numbering system.
Yep.
Now, under the hood, those aren't pulses going over lines and causing gears to rotate.
Yep.
But it's the same addressing system.
That's right. Yeah, and so then there's, of course, 3 digits that precede that, your area code.
Mm-hmm.
And so that essentially said what region of the country you're calling to. And then the middle 3 digits were the office code, or the exchange, as you called it, which is another term that was used, which is, which group of 10,000 subscribers am I connecting to in a local area? And then finally that subscriber number. And so, now with mobile devices, they're just mapped to a subscriber ID, but, they had this very geographically centric kind of hierarchy baked into it. And we don't typically dial it, but there's also a country code, because this then became an international numbering standard.
Mm-hmm.
And so if you see a phone number in the US that says +1, that's the US country code. So if you're overseas, you would dial 1 to address the US, and then your 3-digit area code, your 3-digit office code, your 4-digit subscriber.
That's so cool. All right, well, I'm going to guess where we want to go next.
Okay.
Which is, well, you talked about some of the limitations of this party line concept.
Yep.
Where, yeah, sure, you could dial someone, but then all 12 of your neighbors could listen in.
Yeah, that's right.
Right? And so, I'm aware of some of the solutions to this, but the most obvious one is more wires.
That's right.
But this turns into a pretty bad combinatorics problem.
Yeah, and in the local area, that's actually what they'll do, is just, to this day, the phone company has at least 2 to 4 pairs of wires that come to our house. And so they literally would run, twisted copper wire to every subscriber, and they'd have them in bundles so that at least you're managing, maybe as you go into a neighborhood, kind of a single bundle, and then you would fan it out, at some type of distribution node and send a loop of wire to each house. But fundamentally, it was just more wires. And again, in the local area, they had to connect to everybody, and that was the cheapest way to do it. But as you're connecting offices to each other, and you're building out those trunk systems, or you're going further long distance, what was called tollways or toll calling for long distance, the cost of those wires and just putting more of them in and having enough amplifiers to make sure the signal quality was acceptable starts to become quite high. And And you can find old pictures in cities where the density justified it. And you'll see like these telephone poles that just have crossbar below crossbar below crossbar, each one just laden with wires because they were just wiring the city. But again, thinking back to what we did with the telegraph as well, it would sure be nice to share a common set of wires across multiple callers. And again, the motivation for this was really in the trunking system where you're interconnecting offices, switching offices, central offices. And they used a lot of the same ideas that that Bell was using in the telegraph, which was, well, what if I could use different frequencies of oscillation, of electrical oscillation, different tones to carry different phone calls? The challenge is, unlike the telegraph, which was just on off, here you're trying to capture what we would call the bandwidth or the signal spectrum of spoken human voice, which is not just one signal. It's in fact an entire range of frequencies.
Right, and it itself has tones.
That's right. Yeah, it's composed of tones.
Hard to use tones to carry other tones.
Yeah, and it turns out there's a trick and you can do this, and it's called modulation. And you can take what's called a carrier frequency, and you can use that to itself. So that's going to oscillate at some frequency electrically, and you can use that to carry a separate signal that was originally in a different frequency range, and it essentially will modulate the carrier frequency in proportion to the oscillations of your original signal, your baseband frequency, and essentially now it carries it along at this higher frequency. And then on the other side, you can demodulate it and essentially extract the original signal again, including all of its original oscillations. And again, this is what your radio is doing. And you're taking an oscillating signal, whether it's voice, music, something else, and you essentially shift it up in the frequency range to your carrier frequency for transmission and for tuning of the receipt of that signal. And then you map it back down to its original base set of frequencies for playback or whatever your purpose is with the signal.
Yeah. And there's a couple of things that I think help me make sense of this.
Okay.
And the first thing to know is that the carrier signal has a fixed and known frequency.
Yes.
Whereas the voice that you're transmitting over that carrier signal has frequencies that change based on what's being spoken.
Yep.
You know, every sound I make is just a whole series of different frequencies being crammed in there. And so, you know, in wave math, you can add two waves and you can subtract waves, and that's what's happening. So when you transmit, you're adding the carrier wave to the so I mean, it's not strictly adding, right? But you're essentially adding.
So there's a couple different ways to modulate. And again, going back to people that had a radio, you had two dials in a lot of radios. You had an AM dial and an FM dial. And so the AM dial stands for amplitude modulation. And the idea there is we're going to take that carrier frequency and we're going to change its power level or its volume based on the input signal. So the typical thing here is that the carrier frequency is much higher frequency than the original signal you're modulating. And so as my voice is moving the diaphragm of the microphone back and forth, I'm going to essentially raise and lower the power of my carrier signal in proportion to that. And then on the receive side, I'll measure that power and essentially use that to drive the speaker. So that's called amplitude modulation because amplitude means the magnitude of the signal.
Mm-hmm.
The FM side, frequency modulation, means I'm actually going to, when I transmit this signal, yes, I have a carrier signal, and that's really going to define a center frequency, and I'm going to change the frequency higher and lower in proportion to the waveform that I'm using to modulate the signal. Again, the one that came from the microphone. So as that microphone moves back and forth, I actually raise and lower my carrier frequency within a defined range so that it stays, so it doesn't cause interference with other adjacent channels, which would have their own center frequency. But now I keep a constant power level, but I speed up or slow down that frequency in small amounts relative to the input signal. And then on the receiver, essentially you can multiply that signal by the carrier signal, and you can recover that modulated signal, the original signal that was used to modulate it. And so you can pull it back out.
Yes, exactly.
And again, it all works in the waveforms. It's kind of mysterious,
Yeah.
but it ended up being the basis for
Yes.
for how these things are done.
It is a little mysterious, and it's not actually possible to visualize the physical phenomenon that's taking place here. But we have, of course, come up with all kinds of ways to represent it in 2 dimensions on a graph, and kind of show this sort of thing. But you really just can't see it, right?
Yeah, I haven't found a good way to visualize, especially frequency modulation.
Yeah.
Amplitude modulation, you can kind of imagine the signal getting bigger and smaller as it oscillates.
Yeah.
Frequency where you're shifting it, it's kind of weird.
Okay, so I have to ask a theoretical question, which is a little bit weird, but hey, what the heck? So this phenomenon of modulating and demodulating in the electrical frequency space is possible.
Mm-hmm.
Of course, we use it all. In fact, we're using it right now.
That's right.
At least somehow. Theoretically, the same phenomenon should occur in the audio space as well, in the atmospheric media that surrounds our bodies when we're speaking. Would it be feasible to carry on 2 conversations over the same airways, not radio waves, but over the same pressure waves, and modulate them up and down using some of these techniques?
I think in theory you could. I'm trying to picture what it like acoustic modulator would look like. But yeah, it would be absolutely possible. I just can't picture exactly what the device would look like.
Yeah.
But I mean, if you think about even like an ultrasound, essentially you're using a higher frequency sound wave to go and maybe probe tissue or something like that. But
Right.
I think you could make an ultrasonic transmitter that you modulated with voice band signals and then demodulate it on the other side. I think that would be totally physically reasonable to do.
And that's exactly what I was thinking, is that the range of frequencies that our human ears can perceive is probably too narrow to do this effectively. And so you would quickly get outside that range when you are modulating into a carrier frequency.
Yeah. And in fact, if you wanted to capture the whole spoken human voice, you need that range of frequencies.
Yeah, the entire, right.
Yeah.
The entire audible range.
And that's not our, and you don't need the entire human audible range. We can hear frequencies typically higher than spoken voice uses.
True.
So, yeah.
But it's a lot of that range.
That's right.
Enough of it that you would have to shift out of it for the carrier.
Possibly.
I guess the question is how much would be left over at the top end and the low end of our audible range.
Right. And what would it sound like? So, yeah, if you like pitch shifted human voice up. And again, the reason you do this for a couple of reasons. One of them is if your transmission system can handle higher frequencies better than low frequencies.
Right.
And there are many systems that do this, because the lower the frequency, it means, think about that wave as like rising or pushing forward longer, then it's pulling back as it oscillates back and forth.
Mm-hmm.
A very high frequency wave is moving back and forth very quickly. And as a result, it may be able to transmit through certain conditions better than a very slow, long wave, and it may carry more information with it as it does so.
And have less noise and loss as you go.
Yep, exactly. So that's one reason, is just to match to the conditions you're transmitting through, the physical infrastructure. And then the second one is this, again, really basic way that wave systems work, which is what's called superposition. If you have 2 different waveforms at different frequencies, they can coexist and they add and subtract from each other as they go, but they don't really interfere with each other. And on the other end, on the receiver, you can filter them back out into their respective constituents. And so it provides this mechanism for multiplexing. So if I can take your voice and center it on one frequency and take my voice and center it on a different frequency that's far enough away that when we modulate those 2 frequencies with our voices, they don't intersect and overlap.
Mm-hmm.
We can then transmit all of that together and separate it back out on the other side and recover your voice by demodulating yours and recover my voice by demodulating mine. And so that's what's called frequency division multiplexing.
And this allowed the central offices to have fewer wires between them, right?
Exactly.
Because I don't think our telephones were doing this. The end units that we were speaking into, they were not doing frequency division multiplexing, right?
That's right. Yeah. They each had a dedicated circuit to the central office, but now we're sharing the trunk lines between central offices in potentially a couple of different ways. We're taking turns using them when we make our call. So like if you make a call, you're going to get allocated a trunk when you're done, that trunk is made available for somebody else. So there's like this turn taking, kind of like we had to do with the party line, but managed by the switching telephone system as opposed to managed by us, the customer. And then it may be that those trunks end up actually being combined into a single pair or maybe a couple pairs of wires for a large number of trunks, where each trunk, instead of getting its own pair of wires, is instead allocated some frequency range on a pair of wires. And then when your call is going to use a particular trunk, now that frequency division multiplexer takes your voice signal, the electricity that came in, say from your telephone handset, and it's going to modulate it up to the assigned carrier frequency for your trunk line that's been allocated to you. And then on the receiver, say at the next office that your signal reaches, they'll demodulate that signal. And then, if you were calling someone in that local area, they'll then place that signal on the subscriber loop out to that end party. Or they might switch it onto another trunk to get to a more distant office, say over a toll trunk, at a different frequency.
Yes.
And so your same voice gets modulated, hop by hop into whatever particular carrier frequency was available to you for that next segment.
And these were isolated from each other, so I'm presuming they didn't even necessarily have to use the same modulation techniques.
That's right. Yep. Yeah, they would provide the basic service, which is I'm going to take a voice grade signal from point A to point B, but it turns out, and this is something called abstraction, as long as I delivered the same service to the two endpoints, it doesn't matter what I do in the middle if I still meet the same promise, which is give me a conforming input signal and I will replicate that, on the output side without too much delay, with enough power, without too much noise, then we're all going to be happy.
Yep. And I could do that with 500 wires if I want, or I could do it with 1 and 500 frequencies on it.
Exactly.
And that raises a question for me. Do you know how many different channels a single pair of copper wires were able to carry? Or maybe the number is different for coaxial?
Yeah, I don't know by specifics, but AT&T in the US was the company that really went through this evolution in providing long distance telephony. And in their frequency division multiplexing schemes, I think they had something called a group. And this is where Dave and I are keeping our promise not to do too much research. And I want to say that carried something like 12 voice grade channels. And then groups could be bundled into bigger entities. And at some point there was something called a super group, which I don't know if that was multiple groups or multiples of groups that would take more bandwidth. And that was, again, if you had a higher performance system. So maybe you went from twisted pairs of wires or distinct pairs of wires to maybe a high quality coaxial cable. Think kind of like what you see with your cable TV before that went all digital. And then they figured out how to do this with radio waves as well, using microwaves. So a relatively high frequency radio signal, point to point from tower to tower. Actually, a lot like the wooden telegraph towers we talked about a few times ago.
Different part of the electromagnetic spectrum, though.
That's right. Yeah. No longer the visible wooden spectrum.
The wooden spectrum.
Yeah. Brown.
The brown.
No, yeah. So, and I, as the caller, can't honestly tell if my signal is going over twisted pair, if it's being frequency multiplexed or not, if it's going over coaxial cable, microwave, or later fiber.
Yeah.
As an example. Sometimes there's some subtle hints, like now that we're using computers, you can see how long it took the signal to get to the end and back, and that can give you some clues as to, did I go up to a satellite that's in a high geostationary orbit? Well, that takes a long time, versus did I go over maybe microwave or fiber or copper? But yeah, fundamentally the service was the same. It made a connection, and you could speak and hear and communicate full duplex. At least once you got out of the party lines. I don't know if party lines were full duplex or not, but the standard service people expected was they could speak and hear at the same time to anybody connected to the network.
And remarkably, all of this was done without a single computer. It was electromechanical switching.
Yep.
And electrical components for filtering.
Yep.
And no one ever said the word bit or CPU.
Yeah, they didn't. They didn't know what these things were. And so, yeah, this entire communication network was built all what we would call analog in that sense.
And they even managed to build billing systems on this thing so they could know who was using long distance and how many minutes so they could charge customers for it. Just incredible.
Yeah. I mean, think about, just the sheer infrastructure and all the management side of it. And again, in the US, the American Telephone and Telegraph Company, we'll talk about why they said and telegraph in a little bit, essentially was given a monopoly on the national long distance telephone network through an agreement with the US government. And so they developed all of this technology in-house. And essentially they said, we're going to make this really highly capable, very sophisticated network. And all you got to do is show up with a telephone, which we'll sell you. We'll actually make that too, and plug it in. And so a very simple endpoint device with a tremendous amount of sophistication in the core of the network.
Yeah.
Which ends up being a little in contrast to how computer networks, when those came along, were designed, where they put more of the sophistication in the endpoint device, the computer, and tried to keep the network a little simpler.
They tried, but boy, they're just both really sophisticated.
Yeah, I mean,
by comparison.
Yeah, and of course over time the network has gained
yes
a lot of functions that it didn't used to have.
And now a lot of the network actually is computers, which we'll get to later on that, I'm sure.
Exactly.
Okay, so do we need to transition to digital and computerized voice networks?
I think so. Yeah, let's talk just a little bit about that, and then
or do you want to talk about the telegraph bolt-on first?
That's the thing I'm trying to decide between. And yeah, maybe let's talk about how did telegraphy play into this first, and then we'll go digital.
Okay.
Again, telegraph was invented before the telephone, and multiple companies, Morse had a company called the American Telegraph Company, I think, and then Western Union came along, and they built nationwide and eventually global telegraph networks where you could, send telegrams anywhere around the world. So you could send messages, and we'll talk later about messaging. There were also, I believe, switched telegraph networks where, kind of like we talked about the switchboard to connect two telephones together, that there may have been, for business communications primarily, switchboard-based systems to connect two telegraph operators together, say at different businesses that wanted to, maybe have a conversation about, some contract they're negotiating or something like that. All of this was kind of in place when, in the 1870s, Alexander Graham Bell developed his telephone. By the 1880s, this was being commercialized. And as we talked about, you had to replace a lot of the infrastructure to carry telephone signals because they had higher quality demands. And once you're doing that, and especially when you start frequency division multiplexing and you realize, well, I can put this telephone signal at different frequencies in my spectrum on my wires, well, I can do the same thing for telegraph signals. And in fact...
Yeah, and they need a lot less bandwidth, too.
Yeah, I can use a very small amount of frequency spectrum. The range of frequencies assigned to each signal could be much smaller. So I can actually pack a lot of telegraph signals, like almost for free, into this transmission system in the space that, a phone call wouldn't even use in terms of the frequency range. At that point, Bell's American Telephone Company said, well, we can actually provide telegraph service as well, maybe compete with Western Union. And so they became the American Telephone and Telegraph Company. And this is where the regulations got a little interesting. The US government essentially said, yes, you can do that, but this looks very monopolistic. If you've got both voice and like message-oriented communications. So...
Yeah, and basically, by the way, no extra infrastructure costs for them to do so.
Yeah.
And boom, they can just put any other company out of business because they can do this for essentially no marginal cost.
That's right, exactly. The other service they're delivering, telephony, essentially covers the infrastructure and cost of it.
And to be fair, the infrastructure for telephony was more expensive than the infrastructure for telegraphs.
Yep.
So they did have a big capital investment up front.
Yeah, and the service market was different because most people's homes weren't going to get a telegraph.
Yeah.
That just wasn't the way people wanted to communicate.
Well, yeah, they would have had to build a central office and a switching network, and
yeah,
and they would have ended up with a telephone system.
Right. Well, and think about it, like if everybody got a telegraph key and a sounder, like who's going to use that?
Yeah, no one knows Morse code.
Exactly.
First of all,
so there really wasn't a market. In fact, the way that you would interact with the telegraph was through telegrams. You would bring a message or receive a message. You weren't going to communicate with Morse code unless you were part of one of these systems. Yeah. But for the telephone, now, like every household in America is your market.
Right. That's a big market.
It's a huge market. And so, of course, a lot of dollars in that. And then the government saw not only is this a market, but it's actually a bit of a public service. And we want to incentivize, giving a telephone to those people that live miles from the nearest neighbor where it's going to be very expensive. And so they decided to regulate telephony and make it a common carrier. And in the process, they said, and while we're at it, AT&T, you're going to get this kind of regulated monopoly opportunity, but we're really not going to let you provide retail telegraph and telegram service alongside your retail telephony service. You can still carry the signal for somebody else.
For another company.
You can still be kind of like an infrastructure as a service type company here.
Yes, the original infrastructure as a service.
Yeah, exactly. It's kind of like, I think I've heard that Amazon didn't I don't know how AWS came to be, but I imagined, they built this whole thing and they said just we'll lease out the spare capacity. I've actually heard maybe it was a separate entity that kind of stood up for retail.
Yes, that is a myth, but maybe we could talk about that one day.
Yeah, we should. But yeah, if you imagine it the way I thought it was going to go, it's like, we already have this thing. Let's just go see if we can sell the spare capacity on it.
Right.
Anyway,
yeah.
This was an example of that happening. And they were told no. But the result was that it was no longer necessary or profitable, or at least competitive, for Western Union to maintain their own physical transmission line infrastructure. And so they essentially would have AT&T carry their signals wherever AT&T was available. And then Western Union would just have an office near the central office where all the telegraph signals would be routed to, and then they would do their telegraph thing there.
So they became a Morse code staffing agency where they would just hire people who could work the sounders.
Yeah, and essentially, the message-oriented delivery as well.
Yeah, imagine they had a way to... They probably called people on their telephone to tell them you got a message.
There you go. Yeah, come pick up your telegram. So this idea that voice communication and message communication, digital message communication or text message communication would be on the same network, is really an idea as old as the late 1800s. So then when AT&T was developing better frequency division multiplexing schemes, they made sure that those would accommodate the telegraph. And then as computers started to become available, early digital computers, I think of in like the 1950s, and then the 1960s is kind of when these really got going. And we'll probably talk later about how computers connect to each other to exchange information. There's a number of ways, but one of those ways was to use the telephone system. And so there's a device called a modem, and we've talked about this already, modulator, demodulator, and the combination of those make the word modem. And in this case, the modulation was to make the sequence of ones and zeros, the information the computer wants to transmit, look like the same frequency range of spoken voice. And if we do that and turn it into waveforms that fit in that frequency range, then the telephone system will do its job and carry that signal to the destination. And the demodulator will receive that signal and decode it, demodulate it, and convert it back into that stream of ones and zeros.
And as you may be guessing, the way this works is obviously you have a little speaker on your computer that says the word 1, 0.
That's right.
0, 1. And then on the other end, there's some code that interprets that.
Yeah, exactly. No, I mean, today you could actually build that. That would have been pretty hard to build 50 years ago, 70 years ago.
Yes, with speech recognition.
Yeah, exactly. If we can just solve this problem, we'll have this licked.
No, in fact, I'm sure they came up with a much more clever mechanism to send bits a lot faster than that.
Yeah. Though even, I forget if it was 1950s, 1960s, like people were making computers that could speak, they'd play the waveform that sounded like human speech. So the modulation side on that's not the hard part. It's the demodulation that's hard.
Absolutely.
But instead they would create a different set of tones and adjust those tones in ways that, again, fit within the range of frequencies needed by the telephone system, but could be interpreted on the other side and mapped back into ones and zeros.
Yeah, and if you listen to this, it actually just sounds like static. It's like a sound.
Like white noise. Yeah.
Mm-hmm.
And again, another thing that my kids don't understand is when you connect two of these modems together, they'll initially typically kind of negotiate their capabilities, because you could make these at different speed grades and have different
Yeah.
modulation options, and figure out the quality of the link between them. And so they would start by usually making different kind of tones and patterns of sounds as they negotiated, and then they fall into that white noise mode when they're transmitting, all the information.
That's right. And for those that haven't heard this sound before, I bet you have heard it, and you've heard it in meme form in TikTok videos or YouTube videos where someone stops and is thinking really hard and is confused, and you hear that. It's like that's the modem negotiation sound.
Yep.
Which we used to always hear every time we connected to America Online.
That's right. And so initially these modems, I mean, they were slow. Like, so they could use the whole spectrum of human voice, and maybe they could send like 300 bits per second. And this is called the baud rate. And I don't remember if I think we may have talked about Bado previously. We'll probably talk a little more about them later. And so now that we're digital, you could make this signal hundreds of times per second, and 300 bits per second, 600 bits per second, 1200 bits per second, and so forth. And these would all fit into the single voice channel on the telephone system. And in fact, some of the early modems were what's called acoustically coupled. So they literally did have a speaker, and they had a microphone, and they had like these two sort of rubber cups, one for the speaker, one for the microphone. And you would take the handset of the phone and like push it onto these rubber cups. And so they actually were using sound as an intermediary from the modem's speaker through a little bit of sound in the air to the microphone of the handset on the phone. And then it goes it becomes electrical at that point, goes through the telephone system. And then when the signal comes back out, the phone receives the electrical signal that vibrates the speaker, which moves the air in that kind of hissing sound.
Mm-hmm.
And then the modem has a speaker that the vibrating air activates, and then it converts back to electrical, where it was interpreted by the computer.
The modem had a microphone on the receiving end.
Sorry, a microphone, not a speaker. You're right. Yeah, so the phone had a speaker which fed into the modem's microphone.
And of course, both sides had a modem, and both sides had both a microphone and a speaker, so they could have two-way communication.
That's right. Yeah, exactly. Yep, I wasn't super clear about that. And so from the telephone system, sort of nothing had changed. Like, it was still the same telephone.
Yeah, they had no idea what they were carrying, right? They didn't care if it was human voice or hissing sounds.
Yeah, exactly. We're allowed to hiss at each other, right?
Yeah.
Just happens to be a computer doing it for us. And so that was the initial way. And partly that was technology available, but also AT&T strongly controlled the requirements for their network, including what devices were valid to even connect to it.
That's right. In fact, it was against their policy to build your own phone or buy one from some other brand and connect it to the AT&T network.
That's right. Yep.
I imagine they believed they had good reasons for this.
Yeah, I think as an engineer, they were like, well, I control the whole system. I can ensure I can deliver the best quality to my customer.
But let's be honest about the real reason.
Yeah, it was monopoly.
They really wanted to sell handsets.
Exactly. I'm sure there was a lot of money in that.
Didn't want to give up that business.
Yep. And so they did, as computing became more popular, AT&T kind of tried to get into the digital communication space, and so they did start to build electrical modems that would directly electrically connect to the telephone network, the same way the telephone did, through little electrical plug. And this allowed them to then make higher quality, faster modems, and they still would utilize that same voice spectrum, which was reserved for each conversation. And thus it could float through the frequency division system all just fine, but at higher rates. Again, maybe up to like 1200 bits per second. I don't know if they could do much above that.
Mm-hmm.
And so then in the late 1950s, 1960s, as computers were becoming more available.
Just a little bit more available, to be clear, like still not in households.
Yeah, but at least they existed, and you could put them in significant, physical plant when you had enough capital to do so. Mm-hmm. And as a result of computers being built, other digital circuitry was being developed as well. And so AT&T, I think to their credit, despite being a monopoly, did continue to innovate with the technology available at the time, kind of throughout their history. And so they developed a mechanism to, instead of the long haul transmission of voice telephony being carried as this analog modulated waveform, they said, could we carry it as a sequence of ones and zeros? and actually digitize that waveform. And if you did this, then you just had to get the ones and zeros from one place to another. And you might have better technologies for doing that than this frequency division multiplexing equipment. And again, maybe make something cheaper, maybe use computers or things like them to do this. And so they developed something called T-carrier, and it formed the foundation of the digital telephone network, which just means it was based on ones and zeros as opposed to based on analog waveforms. And they defined this standard where they said, to capture human speech intelligibly, we need to make a measurement of, you can either make a measurement of the speed that the diaphragm is moving in the microphone or the position of the diaphragm over time. And I think you'll get the right answer either way. But we're going to make a measurement of that or of the electrical signal of its, say, of its amplitude, its height, the voltage essentially, or the current. And we're going to make that measurement 8,000 times a second. And there's some math going back to something called the Nyquist sampling theorem that says if we measure at 8,000 times a second, we should be able to fully reconstruct any signal as long as its fastest oscillating frequency is half that, which is 4,000 oscillations per second. And it turns out that if we captured the range of sound from close to 0 to close to 4,000 hertz or cycles per second, we will capture enough of the frequency range for intelligible human voice. And then the next thing they said is, okay, each of those measurements needs to have a certain degree of precision. We'll take each of those measurements and we'll map it to either a number from 0 to 255, or maybe from a negative 128 to positive 127, but we'll essentially map it to one of 256 different possible values. So we have 256 possible values, each being measured 8,000 times a second, and this will give us enough information to reconstruct that voice signal on the other side if we then convert that back into an analog waveform and activate a speaker with that signal.
And I gotta say, I will forever hold these people responsible for the fact that over a telephone, you can't tell the difference between the letter S and the letter F because of this choice.
Because they cut off the high frequency you need to tell the difference. Yeah, that's true.
Yes. But I'm sure they saved money and they found a sweet trade-off economically for that.
Exactly. Yeah, they were trying to figure out how do we deliver this ubiquitous service, and I'm sure they did some tests and said, okay, this is what works for everybody. And of course, that left the opportunity in the future for what we call HD voice now, high definition voice, where you get some of those higher frequency and it sounds more like you're in the same room as the person you're talking to.
Yeah, like the Zoom calls that are today and FaceTime calls and things that are all much higher bandwidth. So you're saying 8,000 per second.
Yep.
Of these numbers that are from 0 to 255.
Yep.
Which is 8 bits. So 8,000 per second times 8 bits equals 64,000 bits per second, or 64 kilobits per second.
Exactly. Yep. And that is defined as a voice grade channel in the digital telephony system.
And whereas the MP3 audio that you often listen to is actually double that. It's like 128 kilohertz or kilobits per second minimum. Usually it's even higher. And so that's why music sounds so crappy over telephones.
Yeah. When you get put on hold and you're like, what in the world am I listening to?
Yes, it's so bad.
Yep. Yeah, it was designed for speech. And again, our human hearing, I don't know what the low cutoff, I think it's something like 20 hertz on the low end up to about 20 kilohertz or 20,000 hertz on the high end is typical human hearing range. So this cutoff and it wasn't even a full 4,000 hertz cutoff. I think I've heard like 3,400 or something like that. It's very low in our total dynamic range that we could hear. And so like music and other natural sounds would sound very limited. But again, the goal was intelligible human voice, not like high fidelity sound reproduction.
And at the risk of rabbit holing here, but you may remember the Sprint commercials from the 90s.
Yep.
Where they claimed that you could hear a pin drop over their network.
Yep.
It was total bull because the sound of a pin hitting the ground is way higher than 3,400 hertz.
Exactly. Yeah, it's going to be a thud of some sort when you take the low frequency part.
They knew darn well that their engineers had chosen to cut that frequency out, and there was nothing that they could do to deliver it better.
Yeah, not over
marketing.
Not over that definition of a voice grade channel.
I still, what's crazy is I still remember the commercials. 1-800-PIN drop. That's what you call if you want to switch to Sprint long distance service.
Yep, I remember that too.
Ah, my goodness.
Anyway, back to so T carrier.
Yes.
So we've digitized our voices and made explicit this cutoff frequency, and the cutoff frequency existed in the analog frequency division multiplex world as well, because you needed to confine each signal to a defined bandwidth, so you knew how tightly you could pack them. How you could have that 12 channel group. How much bandwidth you need for the whole group is going to be defined by how much frequency range you give to each signal. So either way, there's kind of this filter that has this cutoff frequency, but now we're digitally sampling that and generating the 64 kilobit per second signal. And now the idea was, okay, if each voice grade channel is 64 kilobits per second, can I just combine multiple of those voice grade channels into a higher frequency signal? And so they had something called a T1, which was the first level of multiplexing, where they took 24 voice grade channels and combined them, each 64 kilobits, into a roughly 1.5 megabit, 1.5 million bits per second group of these channels. And essentially the way they did it is they said, we're going to take that total capacity of 1.5 megabits, and essentially we'll just round robin between all of these different signals and give each of them an opportunity to send one of those 8-bit samples of the voice that they took, and every one of them is going to get an opportunity 8,000 times a second, and we'll just round robin. And it's called time division multiplexing, where you have this calendar essentially of channel 1, channel 2, 3, 4, 5, and you just go around through the 24 round robin, and then back to the beginning for the next 8,000th of a second. And that was called the T1. And they did provide there were a couple of upshots of that. One of them was, now you could make faster modems, because the digital signal, one nice property it had is once you digitized it, no matter how far through the network you went, no matter how many amplifiers and how many switches you went through, as long as it didn't make errors, the same stream of ones and zeros that you digitized, in the, say, at the central office that the subscriber first connected to, that same stream of ones and zeros would arrive intact at the remote central office where the destination subscriber was listening.
Yes. No new noise from the amplification process.
That's right. So it could be higher quality. It's still frequency limited, which was the lie and the pin drop, but it is potentially a much higher quality. And so this is good for human voice, but it also meant that now computer modems could take advantage of that higher quality, and they could go faster. They could cram more bits of information into that digital spectrum and then extract it on the other side.
And just to wax philosophical here briefly, I think it's very interesting that this digital transmission protocol actually is kind of like a step back to the telegraph days, because now the long distance transmission lines have to worry about noise a lot less, because their job is to recreate ones and zeros in the same way that telegraph relays' jobs was to recreate clicks, with the sounders. And so it's preserved in its pure, pristine, original form at every hop, which means you can go a lot farther without worrying about it. I don't mean farther between amplification and relay steps. I just mean longer overall distance.
Yeah, and exactly, how to regenerate a 1 and a 0.
Exactly.
You don't know how to regenerate voice.
That's right.
But once it's ones and zeros, it's either a 1 or a 0, and you can regenerate it digitally.
So cool.
So maybe just as we almost get probably to wrap up here, probably two things to talk about how a computer could take advantage of this T-carrier system. And then there were also higher order, what were called multiplex structures. So 4 T1s make a T2, I want to say.
Yeah, I think that's right.
Yeah, 4 T1s make a T2, and then I think it was 7 T2s make a T3, or maybe I've got this backwards. I know I'm going to hear from people on this one.
Yeah, T2 was 4 T1s.
Okay.
And then a T3 was...
I think it was 7. I don't know why they chose 7, honestly, but I think it was 7 T2s then made a T3.
Yeah, that is correct. It is 7, based on the data rates.
Okay, yeah. And yeah, you basically just multiply the data rates.
It's like 7 plus some overhead, actually, it looks like.
Yeah, they'd usually add a little bit of overhead to help map what was where, so that the two multiplex switches could sort out what was what. So that T2 then could carry 96 voice grade channels, and that T3 could carry 672 voice grade channels, potentially over one coaxial cable or pair of wires, so much higher capacity point to point than you had with individual wires. So let's talk a little bit about how the computers would use this then. So if I have a voice band modem on my computer, it still has an analog voice connection to the central office. And so it's taking the ones and zeros my computer wants to transmit, turning them into a waveform that represents those ones and zeros in that 300 to 3400 hertz kind of voice signal range. And then at the central office, those are digitized into a different set of ones and zeros that represent that same waveform, the same sounds that my modem sent, essentially. And those are then transmitted to the remote end, where they're converted back into the waveform representing sound waves, and then the receiving modem demodulates those back to the ones and zeros that I sent. So we went digital to analog, and then internally in the network digital for transmission over long distance, and then back to analog at the remote central office, and then digitized by the remote computer. And so we had to fit within the confines of that single voice grade channel. And if you remember, as modems were taking advantage of this, we had our 14.4 kilobit and the 28.8 kilobit, 33.6 kilobit, and they topped out at 56 kilobits per second.
Yeah, which is weird because it should be 64, right?
Yeah, you'd have hoped we could use all 64 kilobits, that 8-bit samples times 8,000 samples per second. But it turns out that AT&T played a trick, which was they thought, if someone's speaking, do they really need all 8 bits of every sample? What if they only had 7? Would they be able to tell the difference? And the answer is to the human ear, no. And so they had something they called robbed bit signaling, which is, hey, I'm just going to borrow that 8th bit from some of your samples to send information about like who's trying to call who, or other information I need to send to control the network.
Mm-hmm.
And I'm not going to make my own channel for it. I'm going to borrow some of yours. And it's kind of interesting that they got away with this, because like, am I getting what I paid for at that point? And again, you wouldn't know until you come along with your modem, and your modem tries to get all 64 kilobits, and somehow that 64th kilobit is kind of corrupt a lot of the time, and you're actually only getting...
Yeah, it's unobtainium.
Yeah, exactly. Try as you might. I was told this was all digital, and yet that one seems like it's noisy. And so you actually really get 7 bits of effective throughput. And so that's why they topped out at 7/8 of that, and they were at 56 kilobits per second.
And even that was a theoretical maximum, because there's loss transmitting between, or translating between audio and digital.
Yep.
But still, it was totally impossible physically to go beyond 56 kilobits per second on your modem.
That's right. Yeah, wherever that raw bit was taking place. There was an alternative, and that was instead of using the voice band modem, where you convert your signal into a representation of those vocal sound waves, the hissing, if instead you directly connected into the network digitally, which is you gave AT&T or maybe Sprint your ones and zeros directly and said, put these straight into my time slot instead of sampling this as a waveform. I just want, here's my 8,000 times a second. I'm going to give you 8 ones and zeros. Just get those to the other end. So an end-to-end digital transmission. In that case, you could get the full 64 kilobits per second.
So they only robbed from the voice grade customers, not from the digital customers.
That's right. So you could pay separately, and this was like a business class service, or it later came to some consumer grade options as what was called ISDN.
Mm-hmm.
I forget what that stood for.
It was like something subscriber digital network.
Yeah, integrated, I think, was the I, if I remember right.
Integrated services digital network, yes.
There you go. And so I think the integrated, I would assume, means voice and data. Integrated, digital, meaning we're talking in ones and zeros. And so now, if you're in an ISDN network, my computer just gives you ones and zeros. And instead of a modem, I have like this digital service unit, but people often called it the digital modem because it did the thing the modem did.
It did a different kind of modulation and demodulation. It just wasn't a voice-based one.
That's right. And maybe your phone would digitize at that point as well. And so then you could carry the full 64 kilobits per second to your destination as long as they had the same quality of service, that same ISDN.
And presumably you could buy multiple of these channels and get more speed.
Exactly. So that was the next thing then is, well, that twisted pair of copper wires going to your house or your office was actually capable of carrying an entire T1.
Mm-hmm.
And so you could, it was called bonding or strapping. You could say, I'm going to take 2 of those channels and I want 128 kilobits per second, or give me 4 of them and I'll have 256 kilobits per second, or so, all the way up to that 1.5 megabit if I was going to use the whole T1 just for digital transmission. And so AT&T enabled all this, and this is what really allowed then the computer-to-computer long-distance transmission speeds to exceed the limitations of voice-grade channels.
Yep.
And to go at computer speeds as computers got faster and faster.
Wonderful. I think that's a good place to stop.
Yeah.
And we're going to pick it up from here, and I promise we will get to the internet, because we just barely teased the internet, but we're going there next, because when you are pure digital end-to-end, it's all internet all the time.
That's right. Yeah, and now, like, who uses their phone as a phone? That's all we use it for, is computer communication, even our mobile devices. So yeah, we'll definitely have to talk about that.
Thank you so much, Shane. This has been enlightening as usual. I loved it.
Yeah, same, Dave. Thanks a lot.
All right, we'll catch you next time on ExplainerCast.
See you then.